Hello listeners, I am Dr. Anuj Kumar Sharma taking this subject from Center for Advanced Studies which is in campus research driven institute of Dr. APJ Abdul Kalam Technical University, Lucknow. So, we are discussing about the fundamentals of mechanical engineering that is the mechatronics. This is important subject from the point of view of the score and to understand the application of different materials in the prototype fabrication or so. So, we should have the basic knowledge of all these things. In previous lecture we discussed about the simple stress and strain. So, we will have a quick recap also before going to the next topic. So, today's lecture is based on the elastic constants. So, we will discuss about different constants and stress strain diagram of brittle as well as ductile material. So, these are the outline of my second lecture. So, we will discuss the stress and strain in very quick way, so that you can recapitulate what we have studied in the first lecture. Then we will come to the various elastic constants, because elastic constant study is very important as far as the application point of view is concerned. Then we will discuss the shear stress strain curve or diagram of brittle as well as ductile materials. So, we know that this is the normal stress. Stress means the resisting force divided by area. Which area? It is the normal area. Then it is known as normal stress, and if it is shear area, or we can say the parallel area, then we call it as the shear stress, right. So, if we try to elongate any body and body generates the resisting force inside the object, then that resisting force per unit area, that is known as the stress, and it is represented by sigma. So, the stress may be of two types. It may be direct and shear. So, this is the direct stress. Direct stress means the force is acting perpendicular to the cross sectional area, then it is known as the direct stress. If we talk about the shear stress, the force is parallel to the surface. Let us say surface is this and the force is acting parallel to this. So, the resistance offered in this object inside this. So, this is the resisting force divided by the area. Which area? This is the tangential area. So, it is represented by tau, and this force is parallel force, and this area is the plane on which the force is acting parallel to the surface. So, this is the shear stress. Now, we will see the strain. Strain is what? So, whenever there would be deformation in the object, either in the terms of length increment or length reduction. So, the overall change in the dimension of that object, means in any direction, divided by the original dimension is equal to the strain. So, like this we generally quantify the deformation in any object in any direction. So, if we talk about the length, then it becomes the linear strain. So, by definition it is epsilon is change in dimension upon original dimension. So, if we talk for the length L, so it is delta L upon L. If it is change in diameter, so change in diameter upon original diameter means delta D upon D, because if you will stretch something, so there would be increment in the length, but at the cost of decrement in the lateral dimension, means the diameter would be reduced to a particular value. So, shear strain means this was the normal strain, means the force was acting perpendicular to this surface. That is why these kind of strains are known as the normal strain, and normal strain may be of two types. One is tensile and another is compressive. And if we divide the strain, so strain may be two types. One is normal strain, another one is shear strain. And what is the basic difference between these two? when force is acting perpendicular, so it is the normal, or we can say the direct strain, and if it is parallel then we call it as shear strain. So, this is a shear strain. Shear strain means this deformation with respect to this, and generally it is represented by phi. So, whatever forces it is generating inside it divided by the deflection. Deflection is how much? Deflection is this C c dash. So, similarly tan phi is equal to C c dash upon the dimension is B c. So, C c dash means delta L or what it is, whatever it is. B c means let us say this dimension is whatever L or so. So, let us leave it. So, this, and for very small values of phi, so this tan phi becomes phi. So, it becomes C c dash upon B c. If we know this value, then we can easily calculate the shear strain. And volumetric strain means change in volume upon original volume. So, let us say we have this object and we compress it by some force. So, it may happen that this dimension may be reduced, this dimension may be increased, this dimension may be increased, but overall if we compress the balloon, so we see that there is a overall reduction in the volume of that particular balloon, and if we blow air inside the balloon, that it might be possible that its overall volume may be increased. So, that will give you the volumetric strain delta V upon V. Now, come to the next topic, it is the various elastic constants. So, these elastic constants are very important, and why these are important? Because irrespective of the shape, irrespective of the size, irrespective of the applications, the materials can be used with the same properties. So, basically materials generally we know by its characteristics. Let us say if we compare the steel with some other material, let us say stainless steel with mild steel. So, there may be two types of material and they may have different applications, right. So, but if you want to compare these two materials, so we should have some characteristics. So, basically these elastic constants are the characteristics of the material which does not depend on the shape and size of the materials. So, irrespective of the shape means ki if you have the wire of the stainless steel, or if you have the plates of the stainless steel, or if you have sheet of the stainless steel. So, these properties would not be affected. So, these properties would be same in all the shapes or sizes. So, before coming to the elastic properties or elastic constants, we should understand what is this Hooke's law. So, Hooke's law, according to Hooke's law, the within the elastic limit, strain is directly proportional to stress. So, if we see strain is dependent on stress. So, it means if we see sigma is directly proportional to strain, or sigma is equal to, when you remove this constant, so it becomes this constant and this epsilon. So, this is the constant. So, here we key stress upon strain, it is always a constant. So, when we stretch any object in the direction of that object, let us say we are stretching it. So, you all might have some experience of stretching a rubber band. So, when you stretch the rubber band, what happens? Its length increased, its length is increased. So, and when you leave the force, then what happens? It try to regain its original shape if you stretch it within the elastic limit. If you stretch a spring, whatever we use the spring in many the objects, day to day use objects like ball pen, if we put the spring and we take out that spring and we stretch that spring up to certain length, then upon the removal of that load it regains its original shape. But sometimes what happens, if we stretch it more or up to a longer distance, then what happens? It loses its shape, it does not come back to the original shape or original length. So, that is the plastic deformation. So, we are talking about the within elastic limit. So, I will discuss more about this limit in the stress strain diagram. So, then we will discuss what is elastic limit, what is plastic region, what is elastic region, we will have a discussion over this. So, according to the Hooke's law, stress is directly proportional to strain. So, this is the when you remove the proportionality sign. So, this we get. So, this is the Hooke's law. So, Hooke's law is applicable up to the elastic limit, beyond that it does not work. So, before that it works. So, it means stress and strain, they have a linear relationship. So, that we will see in the stress strain diagram also. So, there are 4 elastic constants basically which we are going to study in this. So, first elastic constant is modulus of elasticity. It is also known as the elastic modulus, or sometimes it is known as the Young's modulus. So, modulus of elasticity is represented by capital E. So, you have seen it is derived from the Hooke's law. So, within elastic limit, the ratio of normal stress to the normal strain. Normal stress means sigma and normal strain means epsilon. So, the ratio of normal stress to the normal strain, this is the E. So, it means we can write it as E is equal to sigma divided by epsilon. This is the modulus of elasticity. And what is the significance of this? Higher the value of E means more elastic the object is. So, if we the best example is if we try to compare the 2 balls, one ball is of rubber. So, let us say one ball is rubber and one ball is steel. So, which one is more elastic? So, the material which will have more higher value of E, that would have more elasticity. So, elastic means if we try to apply the same force on 2 materials, 2 different materials, the material which comes faster into its original shape, or the material which regains its original shape quickly or faster than the other material, then the material which is attaining its original shape faster, that material is more elastic. So, if we somehow can stretch a steel wire and we released, so it comes quickly to the original shape as compared to the rubber band. So, it means the rubber band is less elastic as compared to the steel, but in practicality we see that elastic means which can be stretched, but that definition is wrong. So, the significance of this E is if we need the material in our design of higher elasticity, then we can select the material according to this. So, high value of E means it can get the original shape or it can regain the original shape at faster rate, right. So, this is the modulus of elasticity. The second elastic constant is modulus of rigidity. It tells how rigid the object is. How rigid means sometimes in many designs we need that our object must be rigid. It should not be allowable to change its shape. So, we want that object to be rigid. In classical mechanics generally we assume that all the objects irrespective of size, they are rigid body, but in actuality they are not. So, within elastic limit, the ratio of shear stress, so which is responsible for the deformation, you can see the planes relative motion with respect to each other or sliding of one layer over the other, they create the shear of or shearing action to the layers. So, within elastic limit, the ratio of shear stress to the shear strain is known as modulus of rigidity. So, if we have low shear strain, high shear stress, then definitely the body will have high shear modulus, and that the body with high shear modulus will be more rigid as compared to the another body. So, it means modulus of rigidity controls the rigidity of the object, how the body is rigid. In many situations we need more rigid body, in many situations we need less rigid bodies. So, according to these selection, irrespective of the shape, if you select any material for a particular application, its G would always be same, right. If it is wire, if it is sheet, if it is pipe, whatever you want to draw, you can draw or you can make, but the value of this modulus of rigidity will remain same. Now, the next property is bulk modulus. Bulk modulus is the ratio of average stress intensity to the volumetric strain, but the only difference is कि now we are talking about the complete volume. So, let us say we have 3 stresses induced on this object in 3 different mutually perpendicular directions. Let us say in this sigma x, in y direction it is sigma y, in z direction it is sigma z. Then the average of these 3 stresses would be how much? If you want to have average, means sigma x plus sigma y plus sigma z by 3. So, this is the average stress. So, sigma generally we call it as sigma AVG, average. Now, so bulk modulus means here it is, please correct it, it is K. So, K is the average stress intensity divided by the volumetric strain. So, if we know this value, then that body would be rigid in overall or in totality. Let us say initially in the previous case, shear stress means the body is rigid in the against the shearing action, but here if we are talking about the bulk modulus, then it is the overall modulus in which we can have the rigidity of that particular object in all the 3 directions. So, likewise we can calculate easily the bulk modulus. So, the unit of bulk modulus is same, stress upon strain, means stress is Newton per meter square and strain is dimensionless quantity. So, it is dimensionless. So, what is the unit of? Unit is Newton per meter square or Pascal. Generally Pascal is very low value. So, we generally apply it to megapascal, gigapascal like this. Now, this is the fourth and the last elastic constant. Generally it is very important as far as the dimensions, change in dimensions ratios are concerned. Poisson's ratio, it is represented by mu or 1 by m. So, it is very interesting to see when you apply any force on the object, what happens to the object. If you are applying the tensile force, then there may be elongation in the object, right, and that elongation would be at the cost of lateral dimension reduction. Here we can see clearly. So, let us say initially the dotted line, it is the initial object. Initially it was having a length of, sorry, the initial object is this. The initial length was L. Now, upon the elongation, sorry, upon the elongation its length has become to L plus delta L with the application of this force. So, it means, and the lateral dimension means this dimension along the length is known as the longitudinal dimension, and the dimension which is perpendicular to the axis of this cylinder, that is this dimension, this is the lateral dimension. So, simultaneously we are seeing that there are changes in the 2 dimensions, one is linear in the linear and another in the longitudinal. So, the ratio, the relation between these 2 strains is the Poisson's ratio. So, there may be 2 types of strains. So, one is the lateral strain, another one is the longitudinal strain. So, the ratio of lateral strain to the longitudinal strain is equal to Poisson's ratio, right. What is the lateral strain? I have already explained. Lateral strain means change in diameter. This is the lateral dimension. So, when you are stretching something, so its length is increasing, but its diameter is decreasing. So, change in diameter divided by the original diameter, that is known as the lateral strain. So, this is the lateral strain, means delta d upon d. So, here it would be definitely negative. So, minus delta d upon d, if we will consider the sign convention, then it will become minus delta d upon d. Now, its length is increasing. So, it means there must be another strain. So, that strain is known as the longitudinal strain. So, longitudinal strain means change in length upon original length. So, delta L upon L. So, these two types of strains are there simultaneously. If we have 3 dimensions, so definitely there would be third. So, that will also be the lateral dimension in the another direction x or y, depending upon the sign convention or the notation. So, if we calculate this lateral strain and longitudinal strain, we can easily calculate the Poisson's ratio. So, Poisson's ratio generally lies between 0.33 to 0.25, it comes in between this range. So, higher the Poisson's ratio means higher the value of lateral strain, lower the Poisson's ratio means lower the lateral strain, right. So, there must be a ratio between the lateral and longitudinal changes of the dimensions, changes in the dimensions of the object. So, Poisson's ratio explains this. Now, these are the relations between these elastic constants. So, this you can try, it is very simple derivation. So, we want to come to this. So, the standard relations between these dimensions is E is equal to 3 k 1 minus 2 mu, and there may be another. So, this is the relation between modulus of elasticity and bulk modulus, and mu means that is the Poisson's ratio. Sometimes it is represented by mu also. So, that is the standard formula which we should remember, right. And another relation is this relation between E, G and mu. So, this is the second relation sorry, E is equal to 2 G into 1 plus mu. So, these are two very important relations. So, we will discuss the derivation of these formulae in the subsequent lecture. So, this was the part 1 of this particular lecture, the various elastic constants and the stress strain diagram. So, we will discuss this in the third lecture also. Now, this is the relation with the help of the previous relations. So, one relation we got E is equal to 3 k 1 minus 2 mu, one relation we got this. So, this is the relation between E is equal E, G and mu, and this is the relation between E, K and mu. So, these two relations we have. So, if we want to have relation between G, K and E. So, if you want to replace the mu, then what we can do? With the help of these two equations, what I can do? I can replace the mu, and I can find out the value of mu from here, that I can put that value of mu in this expression. So, I will get this relation. So, this is the third relation. So, these three are the important relations between the elastic constants, on which the numerical sometimes come directly, or we can be asked to derive the relations, derive the first relation this, derive the second relation and derive this relation. So, we will cover this in the third lecture. Also, we will discuss this in the third lecture, the compressive testing using UTM machine. So, I will try to explain this. So, universal testing machine, UTM means universal testing machine. So, in which you can stretch the element, or this is the upper jaw, this is the lower jaw, this is the upper jaw, this is the lower jaw. In between this specimen is being tight, right, and we apply pull force here and here. So, this machine will try to pull or stretch this object. So, the specimen looks like this. I will have more discussion in the next lecture on this. So, this is the object which is being hanged or which is being attached in this particular machine. So, this is the specimen of the universal testing machine for tensile loading. These are the different, so we generally put point here and here. So, we generally do our observation between this range for this particular length. So, this length is the gauge length, GAUGE, the gauge length, sometimes we call it as gauge length also. So, this is the gauge length and this is the initial diameter, and when you will stretch it in this direction like this we stretch na. So, we are stretching this. So, this is the specimen and we are stretching it here with the help of this machine. So, it is applying some force, tensile force. So, due to that what happens to this I will discuss in detail in the next lecture also. So, these are the type of materials and this is going to happen. So, when you will continuously stretch it, it will a neck will become here, neck will be formed here. So, it will try to break this object from this particular cross section. So, after some time you may get this kind of cup and cone fracture. So, we will discuss it in detail in the next lecture. So, I hope you have understood what is the meaning of stress, what is the meaning of strain, what are the different types of stresses and strain. So, in the next lecture we will see the application of all these things and the discussion on stress strain diagram for different types of material like brittle and tensile materials. So, thank you listeners for your patience and watching this video. Thank you so much.